So welcome to 9-2. We're going to talk about two means, two separate samples, comparing the two means, and the samples will be independent. So in this section presents methods for using sample data from two independent samples being the important part. And we're going to use that to test hypotheses made about two population means, or we're also going to be able to construct confidence interval estimates of the difference between two population means. So let's talk about the difference between independent and dependent. So independent, two samples are independent if the sample values from one population is not related to or somehow naturally paired or matched with the sample value from the other population. I'll give you an example of it in a minute. Two samples are dependent or consist of matched pairs if the sample values are somehow matched, where the matching is based on some inherent relationship. So let me give you an example. Okay, so we'll look at the hint in a minute. Independent samples, heights of men and women. So in Appendix B, or actually you have it in your Canvas, we include the following heights of samples of men and women, and the two samplers are not matched according to some inherent relationship. There's just this sample that we've taken of men and a separate sample that we've taken of women, and they don't know each other. They're not related in any way. Those are independent, okay? They are actually two independent samples that just happen to be listed in a way that might cause us to incorrectly think they are matched. They're not matched. As opposed to a dependent sample, heights of husbands and wives. Students of the author collected data consisting of the heights in centimeters of husbands and the heights in centimeters of their wives. 5 of those pairs of heights are listed below. These two samples are dependent because the height of each husband is matched with the height of his wife. So maybe in general, tall men have taller wives. Shorter men would have shorter wives. So that pairing does mean something, as opposed to just heights of men and heights of women who don't even really know each other. So that should, hopefully you understand the difference between dependent and independent. Let's look at the hint. If the two samples are different sample sizes with no missing data, they must be independent. Well, that makes sense. We can't have something that's dependent and have different sample sizes, because how do we pair them? If the two samples have the same sample size, the samples may or may not be independent. So if the sample sizes are exactly the same, we want to think, are these samples dependent on each other? If the sample sizes are different, they have to be independent. So we have our objective. We can conduct a hypothesis test of a claim about two independent populations, and of course, a confidence interval. So we can construct a confidence interval estimate of the difference between the two independent population means. So we're actually going to look at mu1 minus mu2, the difference in the population means. Our notation is going to be same notation we've had before. So mu1, mean for sample 1. X1 bar is the sample mean. Sigma 1 is standard deviation for the population of the first sample. This is all exactly like we said before. And then we'll have a second sample, a second population, and we have the same notation, only sub 2 instead of sub 1. Okay, so now let's look at our requirements. The values of sigma 1 and sigma 2 are unknown, and we do not assume they are equal. So this is very important, right? So they have to be unknown. They're independent. Both samples are simple random samples, and either or both of the following conditions are satisfied. We've seen almost all of these before, except the two sample thing. So the two samples are both large. So N1 and N2 are both greater than 30, or both samples come from populations having normal distributions. So just like we've seen in the past. Equivalent methods. So the p-value method of hypothesis testing, the critical value method of hypothesis testing, and confidence intervals all use the same distribution and standard error. So they are equivalent in the sense that they will all result in the same conclusions. So we have all these different ways that now that we know how to find out things about our population. And they are equivalent in that they'll give us the same results. So let's do an example. And I have some problems that I've put away. I only actually have one example in this PowerPoint. It should go pretty quickly. So let's see how we do it. Example, are male professors and female professors rated differently by students? So listed below are student course evaluation scores for courses taught by female professors and male professors. So we're going to use a 0.05 significance level to test the claim. So remember the claim that the two samples are from populations with the same mean. So the claim is that the samples have the same mean. Then does there appear to be a difference in evaluation scores of courses taught by female professors and male professors? So the first thing we want to do is we want to talk about our null hypothesis and our alternative hypothesis, right? So we have these two different means, and we want to know, there's two different ways we can write it. We can either say, is mu1 equal to mu2? Or we can say, I'll write it separately, mu1 minus mu2 equals 0. Okay, these are the same. If they're equal, then if I subtract them, we get 0. So now the alternative for this, the claim that the two samples are from populations with the same mean. So that's the same mean. So what's the alternative? It doesn't say anything about greater than or less than, so it must be that it's not equal. So I put in here all my information, and I go here to stat, t-stats, to sample with data, because I've inputted the data, right? So I have values in var1, sample 2 is var2, and I said mu1 minus mu2 is equal to 0. So we're using this form right here. So basically, we're saying then this would be mu1 minus mu2 is not equal to 0. Okay? So this is a two-tailed test. It's a two-tailed test because I either have 0 or I have either my mu1 minus mu2 is 0 or it's not 0. So I can have information down at this end, or I can have information up at this side, right? So that's why it's a two-tailed test. If it was greater than, then I would only have a one-tailed test. If it was less than, I would only have a one-tailed test. but I have a two-tailed test. I want my hypothesis test for this. I hit compute, and here's my information. And so using StatCrunch, and we did actually t-stats to sample with data. Okay, and we output a lot of different things here, right? So we have our, that's our degrees of freedom. We have our test statistic, our t-stat, and we have our p-value. So literally that's what this is right here. So look how big our p-value is. We fail to reject our null hypothesis, okay? Because our p-value is big, our p-value is greater than our significance level. So therefore, we fail to reject. Okay, it's the same as, exactly the same as the last chapter. We could also use a critical value method. So the critical value method of testing a claim about two means is generally easier than the p-value method. With n1 equals 12, so we have, I guess I can close this. So I have 12 pieces of data for n1, and I have 15 pieces of data for n2. And the number of degrees of freedom, always we take the smaller value and subtract 1. That gives us 11. And our alpha is equal to 0.05 in two tails. So we have 0.025 in each tail. And if we go into here, let's do it. So if we want to find out what the t is there, we can go to stat calculators t. And here I have 11 degrees of freedom. I want to know what my t value is on the left side. It's going to give me a negative number. So this is more, oh, there it is. So we get a critical value of t equals plus or minus 2.201, which is what we have here. So this, because it's two-tail, I could also do greater than and put in 0.25. And I'll get the same exact value, only positive. So that's why I have my plus or minus, okay? Now we can see that my test statistic, which is negative 0.660, this is in the rejection area. And this is in the fail to reject area. And that's where my test statistic falls. So the test statistic falls between the critical values. Okay, these are my critical values. The numbers are a little different here. I'm assuming they got that from probably a chart instead of technology. And so the test statistic is not in the critical region, and we fail to reject the null hypothesis. Really similar to what we have already done. I want to give you this formula, not because you're going to use it, because I do want to show you what's happening behind the scenes. So we have our confidence interval, and what we're trying to show is that the difference in simulation means, because there are mu's here, is the difference in the sample sizes plus or minus this error. And this is how we get our error value. Okay, we're not going to be using the formula, so don't worry, but I did want to show you that it does. So if, let's say E equals 2 and X1 bar equals 10 and X2 bar equals 5. Okay, so I would have for my interval 10 minus 5, which is 5, minus 2, and 10 minus 5, which is 5, plus 2. So I know that the difference in my population means is going to be somewhere between 3 and 5. Okay, that's basically, I have a certain confidence that it's going to be between those two values. That's really all that says. So another example, we're going to use confidence interval for male and female course evaluation scores. So using the previous data, which we already have here, we're going to construct a 95% confidence interval estimate of the difference between the mean course evaluation scores for female professors and the mean course evaluation score for male professors. So I go again, stat, t-stat, to sample with data, same as before, var1, var2, and now I'm doing a confidence interval. Now this is a two-tail test. So basically, I'll have some part of it here and some part of it here. So we call this alpha over 2 and this alpha over 2, right? But since what we have is two samples, basically we put in our full confidence interval, which is 0.95, and we hit compute, and we get our lower limit and our upper limit. So we are 95% confident that the limits of negative 5.28 and 0.275 actually do contain the difference between the two population means. Because those limits contain 0, so if I look at what's between these two values, I can see that one's negative and one's positive. So that's my lower limit and my upper limit. Between those two, 0 exists. That means I can't really reject the fact that they could be equal, because if they were equal, then mu1 minus mu2 would equal 0, and 0 is in this confidence interval. So the confidence interval suggests there is not a significant difference between the mean course evaluation scores for female and the mean course evaluation scores for male professors, because it contains 0. Okay, so that's basically what we're going to be doing. I think that's the last slide. So let's actually do some example problems. So question number 1, and I wanted to start a little slowly here. So we have more space. Right. Assume that the following confidence interval for the difference in the mean length of male, which is sample 1, and female babies, sample 2, at birth was constructed using independent, simple random samples. Okay, good, that's all good. What does the confidence interval suggest about the difference in length between male babies and female babies? So we have here negative 0.2 inches, and we have here positive 1.7 inches. But remember that between that negative and that positive is also 0. So that means it could be 0. So really, there is not really any significant difference between these two, the two values in this confidence interval. Okay, that's really what you're looking for. Construct the indicated confidence interval for the difference between the two population means. Assume that the two samples are independent, simple random samples selected from normally distributed populations. Cool, we have everything we need. Also assume that the population standard deviations are equal, so that the standard error of the difference between mean is obtained by pooling the sample variances. A paint manufacturer wanted, so there's a pooling thing in StatCrunch, you'll see it. A paint manufacturer wanted to compare the drying time of two different types of paint. Independent sample, simple random sample of 11 cans of type A and 9 cans of type B. So we know now they're definitely independent because they have different amounts, were selected and applied to similar surfaces. The drying times and hours were recorded. The summary statistics are as follows. So we have these summary statistics. Construct a 99% confidence interval for mu1 minus mu2. The difference between the drying times for paint and the mean. Let's see what that says. And the mean drying time for paint type B. So let's go to stat, tstat to sample with summary. And I'm going to put my information in. So for sample 1, my mean is 71.5. My standard deviation is 3.4. And my sample size is 11. For B, it is 68.5, 3.6, and 9. Now, it tells us here that we can also pool them. It's obtained by pooling the sample variances. So we can hit pooling. And we're looking for a confidence interval. So first, let's see what our H0 and H1 are, because we do need to know whether or not this is a one-tailed test or a two-tailed test, right? So let's see. So we're really looking for the difference between the two drying times. So our first one would be mu1 minus mu2 equals 0. And if there's a difference, then mu1 minus mu2 is not equal to 0. It doesn't say we're trying to see if one is bigger or smaller, and we're not trying to figure out anything about that. So we don't use a greater than or a less than, we just use not equal. So since again, we have a two-tailed test, we come over here and we say our confidence interval is 99% and compute. So my lower limit is 1.51. My upper limit is 7.51. 7.52 really, but I think this is the closest I can come. I check answer, and there we have it. So whenever you have a two-tailed test, let's go back here, because there's something a little tricky in here. So we have a two-tailed test, so our confidence interval stays the same as what we're trying to construct here. So we have a two-tailed test, so we know this is our two tails, and if it's 99%, we have 0.005 over here and 0.005 over here. And if I do it with one tail, if I do it with two tails, I just do this and I multiply it by 2, and I get our confidence, or actually I get our significance level, which gives us our confidence interval, okay? if I have a one-tail test, so let's say it was greater than, then this would be 0.01. And because I have two samples, I would also multiply this by 2. So now I get 0.02, which is a 98% or 0.98 confidence interval. So we'll see that in our homework problems. But I wanted to say one tail, we put for our confidence interval. So our level would be 2 alpha. And if I have a two-tail, our confidence level is equal to alpha. Because I would have had to divide it by 2, but now I'm dividing it by 2, multiplying by 2, so I get the same thing. Okay? So a paint manufacturer made a modification to the paint to speed up its drying time. Independent simple random samples of 11 cans of type A, the original paint, and 9 cans of type B, the modified paint, were selected and applied to similar surfaces. The drying time in hours were recorded. The summary statistics are as follows. So the following 98% confidence interval was obtained for mu1 minus mu2, the difference between the mean drying time for paint can type A and the mean drying time for paint can of type B. What does the confidence interval suggest? So now we're not being asked to actually find the confidence interval. We're given the confidence interval and we want to know what it's saying. So if this is mu, so if type A is mu1 and type B is mu2, then if the drying time for A was greater than, so if mu1 is greater than mu2, then mu1 minus mu2 would be greater than 0. But if mu1 is less than mu2, then mu1 minus mu2 would be less than 0. Okay, so here I have my confidence interval, mu1 minus mu2. Well, everything there is greater than 0. Since it's greater than 0, what that tells me is that, so here I am, is paint type A takes longer to dry than paint type B. So let's see, let's go look now at our answers and pick the right one. The confidence interval includes only positive values, that's true, which suggests that the two population means might be equal. Well, that's not what it says. It says that mu1 is greater than mu2. So I don't see how they're equal. They would only be equal if one was negative and one was positive and there was a 0 in between. So it's not that. The confidence interval includes only positive values, which suggests that the mean drying time for paint A is greater than the mean drying time for paint B. The modification seems to be effective in reducing drying times because we modified type B. That looks like the right answer. Let's just read the other ones. The confidence interval includes only positive values, which suggests that the mean value type drying time for paint A is smaller. No. If it was smaller, then it would be negative. So no. And confidence interval includes 0, which it does not. We can rule that out. So check answer. Perfect. Okay. So listed in the data table are amounts of strontium-90 in milli, whatever that is, or MBQ per gram of calcium in a simple random sample of baby teeth obtained from residents in 2 cities. Assume that the 2 samples are independent, simple random samples selected from normally distributed populations. Okay, so we got all our requirements. Do not assume that the population standard deviations are equal. Okay, so we do not want pooling, right? That's what that means. The only way we want pooling is if they're equal. Okay. Use a 0.05 significance level to test the claim. So hold on, let me get my. So first of all, this is our significance level. And to test the claim that the mean amount of strontium-90 from city number 1, okay, residents is greater than the mean amount from city number 2 residents. So here's what we do. We have H0 and we say mu1 is equal to mu2. And our alternate hypothesis, so the claim is that the mean amount from city 1 is greater than the mean amount from city 2. So I can say mu1 is greater than mu2. Okay. And so I'll pick the right one, but is this a one-tail test or a two-tail test? This is a one-tail because we're greater than. We're not looking at the left side, we're only looking at the right side. All right, so we want to pick the right one and equal mu1 equals mu2, mu1 is greater than mu2. Perfect. Check answer. All right. So let me erase that. The test statistic. Well, let's go over here to our t-stat. Oh, actually, we don't need this. We can actually close this and we want to go here and we want to open this in StatCrunch. And once I open it, there's really nothing I need from here, right? So I'm going to close that. I'm going to go to stat, t-stat, to sample with data. And city 1 is var 1 is values in sample 1, and city 2 is values in samples 2. We already were told that we can't pool our variances, and then we're going to match these. So if mu1 equals mu2, then mu1 minus mu2 equals 0. And here, if mu1 is greater than mu2, then mu1 minus mu2 has got to be greater than 0. And I hit compute. Here's my t-stat. 2 decimals. And paste. There we go. My p-value is 3 decimals. 1, 2, 3. So that's going to end in an 8, isn't it? So I can't do that. Paste it. And I'm going to change this to an 8. Check answer. Perfect. Okay, so now we have to figure this out, right? My p-value, is my p-value bigger? So is my p-value, I'll just put a box, greater than or less than or equal to my significance level, which is 0.05. And my p-value is 0.078. So obviously, that's greater than 0.05. So if I were to look at it on a curve over here, this is 0.05. This is my rejection area. But I'm not in that area because only things smaller than 0.05 would be in there, and 0.78 is bigger. So let me change colors. So I might be right here. This is the fail to reject. Okay. So I know I'm going to fail to reject this. Let's see what the reason is. There is not sufficient evidence, that's true, to support the claim that the mean amount of strontium-90 from City 1 residents is greater. Yes. I can't reject it because I'm not in my rejection region. So fail to reject. There is sufficient evidence. No. When I fail to reject, I don't have enough evidence. I only have enough evidence when I can reject the null hypothesis. So A is the correct answer. There we go. Now we don't need this anymore. Get rid of it. A study was done using a treatment group and a placebo group. The results are shown in this table. Assume that the two samples are independent, simple random samples selected from normally distributed populations. So we have our requirements. And do not assume the population standard deviations are equal. That means no pooling. So we want to complete part A and B below. Here's my significance level for both parts. So we go over here, stat, t-stat, to sample with summary, because they're only giving me summary data here, right? So my mean is 2.32. My standard deviation is 0.57, and my sample size is 25. For sample 2, my X bar is 2.67. My standard deviation is 0.85. And my sample size is 30. We are not pooling. Oh, sorry, we didn't even get the null and alternative hypothesis. So we know that the null hypothesis always has to be that they're equal. So what's the claim? That the two samples are from populations with the same mean. So actually, that's my claim. So if that's not true, then it's got to be. So my claim is that they're equal. So my alternative would be that they're not equal. That's a two-tailed test. So I click that and check. Perfect. The test statistic, well, I think I wrote everything in here already. So I get my test statistic from my hypothesis test. This one is mu1 minus mu2 equals 0. And then this one is they're not equal to 0. We're not trying to find out one is greater or less than, we're just trying to find out what happens if they're not. We hit compute and we get our t statistic, which is 2 decimals. So that's last number is going to be a 2. And my p-value, oh, it's too big as well, to 3 decimals, yes. So we have, that's my p-value. And now what's our conclusion? So we look at our p-value. So our p-value, and then is it bigger or smaller than our significance level, which is 0.10? Well, there's our p-value. Is that bigger or smaller than our significance level? Well, that's definitely smaller. So that means it's going to be in the rejection region. So this is reject. State the conclusion for the test. So it's not fail to reject, it's reject. Reject the null hypothesis. We can only reject if we have sufficient evidence, right? So there is sufficient evidence to warrant rejection of the claim that the two samples are from populations with the same mean. We reject that. There we go. Now we want to do our confidence interval. Now, this is a two-tailed test. So listen carefully because you're going to make a mistake. There's a problem that has a one-tailed test. And it's going to be, remember I said that if it's a two-tailed test, you use the given significance level. If it's a one-tailed test, you have to use 2 times the significance level. Okay, so if this was a one-tailed test, we would have to put in here, I'll show you. So I'm just going to edit. I already have the information here. Why do it again? So now for this one, I would have 0.90, right? If I had, that's because I have a two-tailed test. If I have a one-tailed test, it would be actually 0.80 because each one of the samples has, we take away, we double that significance level. But since it's a two-tail and half of it's landing in each section, and we multiply that by 2, we get the 0.90. We hit compute, and if everything goes well, this is our lower limit to 3 decimal places. That last number is going to be a 3. And my upper limit, 2, 3, that stays the way it is. And check answer. Very good. So I don't want to go to the next question yet because I want to show you that here we rejected the null hypothesis, which meant that the sample sizes are not equal. This shows me that mu1 has to be smaller than mu2 because everything here is negative. Actual population mean is smaller for treatment than for placebo, okay? Because it's negative. And if mu1 is smaller than mu2 and I subtract them, then I'm going to have a negative value. So that's basically what's happening here. The last problem, I'm not going to do completely because it is in your homework, but I did want to show you something that I didn't think that you knew. So I'll show you what I mean. When I click here, I'm getting here. So if I download this, I'm only getting part of my information, right? So you saw before that when I go to stat and tstat and to sample, I either pick with data or with summary. But here I have data on the left and summary on the right. What do? Well, the best thing to do is go to summary stats column, and we want bar 1. And what do we need? We need n. We need the mean, and we need the standard deviation. And also, I can come here and I can store the output in there's my output right there. Okay, there's my N, my mean, and my standard deviation. So now I can compare summary data, and that's all I'm going to do. So you have the summary data from the left side, and you have the summary data from the right side. And from here, I'm going to let you guys finish this problem, but I do want to show you this. And that concludes everything. So good luck. And if you have any questions, please feel free to ask. Have a good one.